And we're going to start out really simply by finding the area of this triangle. Hopefully this isn't too insulting to you because you've known for years that it's 1/2 base times height. And with the base being 4 and the height being 18, I think it's really obvious that the answer is 36 square units. But we're about to take a huge jump in your mathematical life. What if the hypotenuse wasn't a hypotenuse? What if it wasn't straight? If you use this parabola instead, you're still going to have a 4 and an 18. These points will be 0, 2, and of course 4, 18. You can verify that by plugging them both into the y equals x squared plus 2 equation. They do work. But that's not going to have an area of 36 anymore. In fact, the area should be smaller, at least that's my feeling. And here's why. If you were to connect this to make a triangle, you can see that, yeah, sure, you gained a little bit of area here in the corner, but man, you lost a lot of area that turned white here. So instead of being, 36 like it was on the first page, it's probably going to be low 30s, maybe even upper 20s. And for years and years and years, mathematicians tried to figure out how to find the area of curvy shapes, and they couldn't. Until one day, a man named George Riemann had a breakthrough idea. He decided to divide this region into 4 partitions. And each partition was an equal width. So in this case, they were all 1 apart here on the bottom. And obviously these points would start with 1s, 2s, and 3s. If you plug those into the original equation there, the x squared plus 2, you would get 1, 3, 2, 6, 3, 11, and of course the 4, 18 that we already have. All right, so here's what George Riemann decided to do. He started out from the left-hand side and made rectangles, like so. Just went straight across. And to this day, they're still called Riemann rectangles. Some people say Riemann, by the way. I've heard it both ways. And then what he did is he found the area of each rectangle right here, and he added them all together to get the total area. And since we're coming from the left-hand side, we call it left rectangular approximation method, or LRAM. All right, the first rectangle is 1 by 2, that'll be 2, plus. The next rectangle, this one I'm circling right here, is a base of 1, a height of 3. 1 times 3, of course, is 3. Then you have 1 times 6, and finally 1 times 11. That's going to add up to 22 square units. And of course, that's way, way too low because you're not counting a whole bunch of orange stuff that you want to count, or peach, whatever that color is. You're missing out, and he realized that. So what he did is instead, he decided to come from the right. So he came from the right and made rectangles, like so. And as you can already tell, these rectangles are going to provide an overestimate because when I color them in, we're going to count a bunch of white stuff that we really don't want. And he knew that too, he realized. And not surprisingly, RRAM stands for right rectangular approximation method. All right, our first rectangle now is 1 by 3 because the height of that is 3, so the 2 doesn't get to be used. Plus 1 by 6. In fact, you can just take all these y coordinates right here. 1 by 11. 1 by 18, that adds up to 38 square units. 38. And so George Riemann boldly proclaimed, I've got the area of the curved shape. And everybody was like, oh man. He's like, it's somewhere between 22 and 38 square units. And people, of course, were majorly disappointed by this. They're like, oh, that's not that impressive. And so, yeah, back to the drawing board he went. Instead of making 4 rectangles next time, he made 8. He made them, half as wide. And he got a better approximation. Instead of being between 22 and 38, maybe it's between, 25 and 35. And then he made 16 and 32, and he made more and more rectangles. And pretty soon he was starting to make some progress. He's like, hey, I've got it. It's between, 29 and 30. And then he died. Unfortunately, he only lived 40 years. And adding up all these numbers, it's very time consuming. And so his work was just kind of there, but it wasn't finished until calculus came along. Sadly, calculus was actually being invented before a lot of his work, just because there was really no communication in Europe yet or anywhere in the world. We didn't have the internet, obviously, and so people couldn't collaborate. But the people that were working on calc and inventing and discovering calc, Isaac Newton, Gottfried Leibniz, were able to confirm their theories by using all of George Riemann's hard work, all his calculations, and they found that, yeah, we can find area of curvy shapes by integrating, which is what we learned last section. So this is actually coming together. This is a huge development. All right, let's take a look at some modern technology. So I went ahead and got onto Microsoft Excel and went ahead and made his creation. A is 0, B is 4. A and B are the left and right boundaries of the orange region that you saw. And then I devised a formula that would figure out all the x and y coordinates. You can see them in the box. Those are the same points that we had. There's the 418. And I came up with the LRAM and RRAM, the same LRAM and RRAM that he created with his 4 rectangles. But as I increase the number of rectangles, things get interesting. Here's 8 rectangles. By the way, N is the letter that we use for number of rectangles. As you can see, I still have the 0, 2, the 418. I still have my normal points, but I have points in between them. You have to remember that George Riemann was adding this all without a calculator, so obviously any slip-up would ruin all his life's work, so it took him a while to get these numbers. And 25.5 and 33.5 still are pretty far apart. So again, he went to 16 and then 32 rectangles. I went to 200 rectangles. Check this out. As you can see, we're adding a whole bunch of things together. This would take years to do. And we have an idea that the area of that curved shape is probably 20, well, it is 29 point something. We're closing in on it. And again, George Riemann just didn't have the time to be able to do this. Let's go all the way to 10,000 rectangles. Oh my gosh, look at this thing. Can you imagine adding all that together? That's crazy. I'm still not even to 2,000 yet. If you take it all the way to the bottom, you can see we made it to 418. Oh my gosh. But we've got the answer, or we're starting to get the answer cornered in between 29.3301 and 29.3365. It turns out the actual area of that shape is exactly 29 1/3 square units, which for a curvy area to come out with a fraction like a 1/3 was startling to me at first. But that's what it is. And notice, this is important, that the actual area is not exactly halfway between LRAM and RRAM. If it was a straight line, that would be true, but the graph had a curve in it, so it's never going to be halfway. In fact, I'll show you today how to get to 29 1/3. I'll show you right now, even though I'm not supposed to tell you guys yet. This is working ahead a bit, but you know enough math that it's going to make sense. All we need is the x squared plus 2, and we need to realize that we start at 0 and we end at 4. I'm going to show you little snippets of section 4.3 and 4.4 right now, but here's the actual area of the shape, which of course we already know is going to be 29 1/3. The area is the integral. This is a huge moment. But this time, instead of an indefinite integral with a plus c at the end, it's a definite integral We take the a and we put it as the lower limit of integration. The b goes up top. So we're integrating, and the way you say this is the integral from 0 to 4 of x squared plus 2 dx. Let me say that again. Area is the integral from 0 to 4 of x squared plus 2 dx. All right, even though I say the 0 first, I plug the 4 in first. So the way you say it and the way that you do it are opposite of each other. That bothers me, but hey, again, I didn't invent this. I didn't make it up. We're just sort of stuck with it. Okay, here's what we do. We integrate. So the x squared up by a power will be x to the third, as we know. Divide by the new power, so that just be a 1/3 in front. So 1/3 x to the third, plus, and again, same thing here, 2x. But no plus c this time. Instead, we do this. We put this vertical bar, we put the 0 and the 4 out here. Now, old habits die hard. My calc teacher, instead of a bar, would make a bracket, and he put another bracket on the other side. This is not conventional, but since I was brought up with it, I'm kind of used to it, and I feel comfortable. I kind of like the 1/3 x to the third plus 2x, sort of nestled inside its little home with its brackets. I'm one of the few teachers that would ever write it like that. Most people just put a single bar down the right-hand side and they're done. So just so you realize that what you see from me is not typical. But I like my brackets. Like I said, old habits die hard. I'm gonna keep them. All right, here's what you do. The 4, the upper limit, goes in first. So you take the 4 and you place it here, and you see what you have. 4 to the third. 4 times 4 times 4, that's going to be 64. Times 1/3, it'll be, 64 thirds. Plus 2 times 4, that's easy, that's 8. And then in between, we go minus. It's always a subtraction. Why is it a subtraction? Because Isaac Newton said so, and Gottfried Leibniz, the discoverers of calculus, realized that if you put a subtraction in the middle, it works. Now it's 0's turn to play. 0, get yourself in there. And it makes 0 plus 0, which of course is a waste of time, but I had to try it because it's a good example. 64 thirds, that's 21 and 1/3. Okay, plus 8. Oh my gosh. That's the 29 and 1/3 that we got from 10,000 rows of Microsoft Excel. And that is the exact area of that shape. Unbelievable. So you can start to see the additional power of calculus. Before today, you guys only knew how to do the area of, I don't know, less than 10 shapes. You figure rectangle, triangle, square. Actually, squares are rectangles. Trapezoid, on a good day, maybe a rhombus and a kite. Parallelograms. You were really limited. Now you can find areas of any shapes. Any shapes without names even, which is really cool. I mean, you don't want to be the architect who can only make square buildings. A lot of things have scalloped edges. You have to figure out areas and volumes of weird things, and we're on that path. This is cool. All right. The thing I showed you right now has a name. It's called the first fundamental theorem of calculus. We're going to learn it formally later, but I was so excited I couldn't keep the secret. I had to show it to you. All right, there's one more thing I want to show you, a piece of technology. We're going to go there now. It's GeoGebra. So you can see I typed in the equation y equals x squared plus 2. Everything else is a 0. And then I decided how many rectangles to make. I made 4 rectangles. And again, you can see the actual answer. There's the 29 and 1/3 that we had. But it says show left rectangles, right rectangles. So this first one is the LRAM. The second one's the RRAM. Later on, we're going to do midpoint rectangles, which will be MRAM. And then finally, section 4.6, we use trapezoids. It's called trapezoidal rule. We're going to wait on that one. But yeah, this is kind of cool. If I do an LRAM, you can see there's that 22. If you do the RRAM, There's the 38. You can see that's an overestimate. What's cool about this, too, is you can see that if you change the n, I'm just going to let the n go up by 1 each time. So there's 5, 6, 7 rectangles. Look what happens as the rectangles get skinnier and skinnier. The answer for LRAM gets closer and closer and closer to the real exact answer of 29.333, 29 1/3. In fact, by the time you hit 25 rectangles here, you can hardly see the mistake. You know, there are regions that are being left out, but man, it's hard to even see them. Wow. You get a very accurate, I mean, you know, by the time you get up to 40, 50 rectangles, you can't tell there's anything wrong with this, even though we're still not quite to the answer yet. So that's really cool. That's the whole idea of integration. That's why I said when the integration symbol looks like a stretched out S, it is a stretched out S. It spells sum, and you're taking the sum of a bunch of super skinny rectangles. That's exactly what's happening. And if the rectangles become paper thin, you're getting a really great, accurate answer. You can see with the right rectangles as well. If I start this in motion, and you get skinnier rectangles and more of them, you can see that the blue that's hanging out above the curve that shouldn't be there is starting to disappear. The mistakes are going away, and the right sum, also called RRAM, is starting to approach the 29 1/3. Even with just, 30 rectangles, you're already getting very close. You're already within about a block or so of being right now. And so this is powerful. So again, you can now find the area of any shape. And when this was a triangle, remember way back when that's all we knew, in the example number 1, the answer was 36. And I said, I think this is going to be in the high, 20s, low 30s. I was right. It was in the upper 20s, 29 1/3. That seems about right. I can only imagine if George Riemann could see this modern technology and see his whole life's work done in about 5 minutes. He'd be like, what? I think he'd be like thrilled and angry, both kind of at the same time. Hopefully more thrilled. All right, let's move on. All right, we're going to use LRAM, RRAM, and MRAM, which again stand for left, right, and midpoint rectangular approximation method, to approximate the area of that purple region. Okay, let's see what we can come up with. First of all, we're going to divide it into 4 partitions. Notice it says n equals 4 subintervals. So I'll do that now. Complete with labeled points. And we'll start off with LRAM. And again, left rectangular approximation method means just that, start from the left. So I'm going to start from the left. And then we would shade in these 4 rectangles. All right, the width of each of these rectangles is 2, because you're going from 1 to 9, and there's 4 of them. So it's, 8 divided by 4, of course, would be 2. I'm going to factor the 2 out. All right, the heights of the 4 rectangles would be the 12. These are just the y coordinates. 4, 12 fifths, and 12 sevenths. It seems unfortunate, but this 4/3, I should say, at the end doesn't get to participate in the LRAM. Don't worry though, 4/3. When we get to RRAM, you'll get to have your chance. Working this out is going to give us, inside at least, 704 over 35. 704 35ths. Multiplying that by 2 will give us 1408 35ths. And of course, since we are in AP Calculus, rounding things off to 3 places minimum is always totally acceptable. And 1408 35ths is approximately 40.229. Okay, so that is LRAM, left rectangular approximation method. Let's try RRAM next. With RRAM, we come from the right. So this is going to be an under approximation. We're basically taking these rectangles and adding up their areas. Again, each rectangle has a width of 2, just like before. That will stay consistent between LRAM, RM, and MRAM. But this time, we don't use this 12 anymore. The very first rectangle has a height of just 4. And all the other numbers get used again. 12 fifths, 12 sevenths. And this time the 4/3 gets its chains. This inside is going to work out to 992 over 105, making the final answer 1984 over 105, or 18.895. Again, in calculus, remember, if you go decimal, you have to go at least 3 places, minimum 3, and you can either round or truncate. All right, we're going to try MRAM next, which is new. This is the midpoint rectangular approximation method. For MRAM, you still use 4 partitions. They're the same partitions, but instead of starting from the left or starting from the right, you start from the middle and you go both directions. You start from these middle locations and you go left and right. So what's happening is, instead of overestimating or underestimating the area, it's a simultaneous over and under approximation. Let's go ahead and get those points right here in the middle and see what they are. Instead of using the odd x coordinates like 1, 3, 5, 7, 9, we're going to be using 2, 4, 6, 8. Okay, let me put the MRAM rectangles back in. All right, there we go. Once again, like before, width of 2 for each rectangle, and the heights this time are 6, 3, 2, and 1.5 or 3/2. This is going to work out to 2 times 12.5 when you add those numbers in the parentheses up, which is 25 square units. And honestly, that's probably the closest approximation to the real answer that we can come up with.